Next, we're going to talk about a comparison rule for infinite limits of sequences. So suppose we have two sequences, an and bn, and suppose that they have a relationship to each other so that the terms of the sequence an are always less than or equal to the terms of bn. Now, if it should happen that the lesser of these sequences, an, diverges to infinity, so the terms of an itself gets bigger and bigger and bigger and bigger without bound. Now, then it will also be true that the greater of these will sort of be pushed off to infinity by the lesser, and it will also have an infinite limit. So the idea here is if you have a lesser and a greater sequence that obey this inequality, if the lesser sequence diverges to infinity, then what could the greater sequence possibly do? It must also diverge to infinity. This is super easy to prove. Let me remind you of the assumptions. So we are assuming here that for every cap n, there exists a cap n such that for every natural number little n, then if little n exceeds cap n, then we're assuming an is greater than cap n. And the goal here is the same as it applies to the sequence b, which is greater. I should have put an implication there. So this thing implies bn exceeds m. So this is what we're assuming about the sequence an, and this is what we're attempting to prove about the sequence bn. So how do we prove this? Same way we always prove this. Let m be arbitrary. So I'm going to leave a blank line here, and then I'm going to eventually fill this in and edit a little bit, but that's to be expected. And then this is just boilerplate stuff. Let's let n be in the naturals, and we're going to assume that n exceeds cap n. Then what do we need to prove? Well, I've left a whole half board for this, but it's not going to take this kind of space. We need to prove that bn is greater than m. So bn, how are we going to show that bn is greater than m? Well, we know one thing, exactly one thing about bn. We don't know a formula for it or anything. The only thing we know about bn is that it's greater than or equal to an. But we've assumed something that allows us to say that an is greater than m. So let's say that this is greater than m. But now hold on a minute. We've assumed this entire thing, which says for every m, there exists a cap n. So we're not this doesn't just tell us that an is greater than m. It tells us that we may invoke the definition of the limit. So in order to say that an is greater than m, we need to actually have an invocation of that, and we need to have the assumption that n is greater than the cap n. So what we're going to do is we're going to fill that in here. So we're going to choose cap n for m in the definition of the limit of an is infinite. And then here, the cap n that I need for b has to be exactly equal to the cap n that I need for a, because there's nothing more that I require, right? I don't furthermore require it to be greater than 20 or anything like this. This is the only requirement that I have on the cap n that I'm trying to choose for b. And so what I'm going to do here is, instead of saying like choose an n1 and then cap n is equal to n1, I'm just going to erase this line, and this line will be my choice that suffices for b as well. So basically, the definition here is supplying me with a cap n, and I am just using it directly as the cap n that I am justifying the existence of in this statement. So choose cap n for this. That is my entire choice of the cap n. And then this is true because little n is greater than the cap n here, and then that's as desired. So this proof is now complete. So let's check to see whether we've done this logically. Have we reasoned about an arbitrary n? Yes. Have we shown that an n exists? Yes. Have we reasoned about an arbitrary n? Yes. Have we assumed that n is greater than n? Yes. And have we justified these inequalities? Bn is greater than m? Yes, we have. So, so this is a correct proof of the comparison test. Notice, however, this is a very asymmetrical thing. If an diverges to infinity, then bn does as well. If bn diverges to infinity, well, then I know nothing particularly about an, right? It could converge, diverge to infinity. It could do anything, basically. So this is a one-way street, very much. However, it can be used backwards in one way by simply using its contrapositive. If we know that Bn does not diverge to infinity, for example, if we know that Bn is bounded, then we can at least say that An does not diverge to infinity. But remember that knowing that An does not diverge to infinity, there are still several options for what it could do. It could converge to a real number. It could just diverge, but not to infinity. It could diverge to minus infinity. There are a lot of options for what An could do. So this is very much a one-way street. So this is our comparison test. Now the next law that we want to show when it comes to divergence to infinity is the relationship between the infinite and the zero. If a sequence gets larger and larger and larger and larger, and you take reciprocals of the values of those sequence, then we would expect that those reciprocals would get smaller and smaller and smaller and would converge to zero. This is an interesting statement because it involves the two different forms of the limit being equal to a certain real number, zero, and the limit being equal to infinity, which is really code for the sequence getting larger and larger and larger. So what I want to do is I want to state and prove this law for reciprocals and their behavior about zero and infinity next. So let's call this the reciprocal law. So we're going to need a sequence. Let An be a sequence. So then let's say of positive numbers. I'm just going to make them positive numbers because it'll simplify some of the computation. So let's take a sequence of positive numbers. Then then the limit of An is equal to infinity if and only if the limit of the reciprocal 1 over An is equal to 0. So in other words, a sequence will get larger and larger and larger if and only if the corresponding sequence of reciprocals is getting smaller and smaller and smaller and approaching 0. This is if and only if. So if you know this, then you can deduce this. So let's go ahead and prove this. So we'll have two directions to prove. We'll have to assume this and prove this, and we'll have to assume this and prove this. So let's go the forward direction first, because that's the natural thing to do. So, so proof, and then we'll go the forward direction first. So we'll assume, what are we assuming? We're assuming this, which means that we are effectively assuming for every m, there exists a cap n, such that for every n in the naturals, if n exceeds cap n, then An exceeds m. And the goal then is to show the traditional, so this is a traditional limit, right? This is an actual real number, so this is the epsilon definition. So the goal is to show for every positive epsilon, there exists a cap n, such that for every natural n, if n exceeds cap n, then now I have to use the traditional definition of limit convergence. So I have to take 1 over An, and I have to subtract 0, and I have to take absolute values, and I have to say that is less than epsilon. So notice this is the usual definition of the limit, and this is the new definition of divergence to infinity. So that's the statement of the assumption and the goal, and let's get to proving. So how do we prove this goal? Well, we let epsilon be arbitrary. So let's let epsilon be greater than 0. And then as usual, I need to choose a cap n, and as usual, at this stage in the proof, I don't know how to do it, so I'm going to leave that blank. But after doing it, then as usual, I can simply say, I need to prove something for all little n, so let's let n be natural and assume it's greater than cap n. Now, here I need to prove that this is less than epsilon. So what I'm going to do is I'm going to say then, and I'm going to start my computation. So absolute 1 over An minus 0, absolute. I kind of missed. So minus 0, absolute. And then here, because I am proving a traditional limit, I do intend to end with less than epsilon. And so this is where I would do a whole bunch of computation. If I were doing some ugly algebraic example, I need to get this thing less than epsilon. Now, let's simplify as much as possible. Minus 0 is redundant, so the first thing I want to do is I want to throw that out. Now, because of the simplifying assumption that these are positive numbers, their reciprocals are also positive numbers. 1 over an is a positive number, and the absolute value of 1 over an is also a positive number. So, well, who cares that it's positive? I already have the absolute value signs to get rid of that, but it matters because it gives me permission to completely discard the absolute value signs. So then I can simply discard the absolute value signs, and I can say 1 over an. So basically, I want 1 over an to be greater than epsilon. Now, let's throw in a little bit of scratch work here, and we'll see that 1 over an is less than epsilon. I think I misspoke. 1 over an is less than epsilon if and only if, multiply both sides by an and divide both sides by epsilon, if and only if an is greater than 1 over epsilon. So this is actually a little bit unusual. If I were doing a traditional limit proof, I would expect here to have a statement about n. N is greater than something, and then that statement of n is greater than the square root of something, then that would go here, right? Because I would need the n to exceed whatever value it was, and I would put it there so that this assumption would activate. Here, however, I don't get a statement about n. I get a statement about an. An is greater than 1 over epsilon. So in order to get this thing less than epsilon, I need an greater than 1 over epsilon, but I don't know what that means about n. Well, how can I get an greater than a certain value by any choice of cap n? I can get that if that value is m. And so here, this informs a choice of m in the assumption here. What I'm going to do is I'm going to guarantee this equation, an greater than 1 over epsilon, by using 1 over epsilon as a value of m. So let's do that. So how do we do that? It's time to invoke this. So what I'm going to do is I'm going to choose n for m equals 1 over epsilon in the definition of the limit of an is infinite. And this is a valid choice because notice that it depends upon epsilon and nothing else, and epsilon has been chosen at this moment in the proof. Now, what does that mean? When I choose cap n for that, what that means is whenever I have a little n greater than cap n, I will be assured that an is greater than 1 over epsilon. So that's exactly what I need. So let's just throw in a little note here. Note, an is greater than that n implies that an is greater than 1 over epsilon, which is exactly what we need here. So this thing, so as in the previous proof, where I did the comparison test, I had to choose a cap n, and then I realized that was actually the only requirement that I needed. And so what I'm going to do is I'm going to erase this, and I'm going to let that choice be the choice of the cap n, the only choice that I need in this example. And then this is going to be less than epsilon because an is greater than 1 over epsilon. So this is a little bit of scratch work here. And then this completes the proof of the forward direction because this is the intended absolute difference being less than epsilon here. And that gives us the forward direction as we've desired. Now, we still have a backward direction to do, so let's get started on that. So I think I'm going to erase this stuff and switch around the goal and the assumption. So for the backwards direction, I'm just going to change this to, we're proving this backwards. And now this statement will be our goal, and this statement below will be the assumption. So now we're assuming that the limit of 1 over an is equal to 0 and attempting to prove that the limit of an is equal to infinity. So we're trying to show this. So if this is our goal, then we have to start with an arbitrary cap m. So let's do that. So let's let m be positive, well, be any real number. And as usual, I don't know how to choose n, so I'm going to leave this blank. And what we'll do is eventually we'll discover that there's only one choice, and we'll do the same thing we did last time. But that's okay. I just want to communicate that we are as yet ignorant how to perform this act, but that's okay. We're going to continue anyway. So then we're going to let n be a natural number, and we're going to assume that little n is greater than cap n, as usual. And then the goal, of course, is we're going to try to prove that an is greater than m. So an is supposed to be greater than m. So that's what we're trying to prove. Now, how on earth are we going to use this ugly assumption? Well, you've already seen from the forward direction that there seems to be a key relationship here between the value of cap m and the value of epsilon. And the relationship that was suggested by the last proof is that the connection between this cap m and this epsilon is that they themselves are reciprocals of one another. And so that suggests already what we should do in the first place. We should just apply this where epsilon is 1 over m. So let's actually go ahead and do that. And that will give us a choice of cap n. So let's choose cap n for epsilon equals 1 over m in the definition of the limit here. Let's see here in the assumption in the definition of the limit an is equal to 0. So that is here. Let's just write down what it is we do know about this sequence, which is we do know this. So we know that 1 over an minus 0 absolute is less than epsilon. Sorry, not epsilon. We know that it's less than 1 over m because we have chosen cap n for epsilon equals 1 over m in the definition of this limit. And so we've basically applied this definition to the value 1 over m. So what does that mean? That means that the absolute value of 1 over an is less than 1 over m. Now, 1 over an is a positive number because an is a positive number. So we may safely drop the absolute values. And now we have a positive number less than another positive number, and we may take reciprocals. But when we do take reciprocals here, the sign of the inequality changes from less than to greater than. And this is actually exactly what we're trying to show, right? This is the end state for the goal. So here we've just taken the content of this assumption about n, and we've ended up just deducing the goal directly from that assumption without any significant chain of inequalities going on. So we can erase this line. This was apparently the only requirement that we needed for cap n. And so this establishes that if we have this statement, if the limit of 1 over an is equal to 0, then indeed we get an diverging to infinity. So this shows that we have a really nice relationship between a positive sequence converging to 0 and the reciprocal of that sequence diverging to infinity. This is really convenient because we can say, we can use our traditional ways of thinking about limits converging to 0, trusting that that's a traditional limit. And then we can make deductions about other sequences diverging to infinity, which is convenient to be able to do.